I am honored today to introduce to you Dr. Christian, our next speaker. The list of his accomplishments is very, very long, and I'm afraid that if I went through the whole long list, my speech would be longer or almost as long as his lecture. So you'll excuse me if I cut it short. He obtained his bachelor, master, and PhD degrees from MIT. He worked for Stone & Webster Engineering in Boston, where he raised to the position of vice president. And he's been a consulting engineer in Boston since 1994. He's a member of the National Academy of Engineering, an honorary member of the ASCE, and as you know, the 2003 Terzaghi Lecturer. He served as the editor-in-chief of the ASCE Journal of Geotechnical Engineering, and he's author of over 100 technical papers on a variety of topics. And reading his curriculum, I can say really a large variety of topics. It would take longer for me to say what these topics are than say, basically, he worked on everything possible in geotechnical engineering. He is also the co-author of 3 books, the latest of which is Reliability and Statistics in Geotechnical Engineering, for which effort I am very grateful, because I think geotechnical engineering future is that way, and it must have been a humongous task, and I'm happy he did it, and we can just enjoy the benefits of learning from his work. At this point, usually the person that gets this job that I have now says, and when John and I were in graduate school, and goes on with a funny anecdote from those times. Obviously, Dr. Christian and I were not in graduate school together. In fact, everybody here knows I'm a Berkeley graduate. I didn't go to MIT. We met for the first time last night at dinner, so I don't have any personal anecdotes to tell you. But I learned something last night, and what I learned is that today it's a bit more special delivery of the Terzaghi Lecture for Dr. Christian, because his brother and his nephew are going to be in the audience. And so I would like to welcome them if they made it over here, or maybe we can welcome them later when they arrive. But without any further delay, please welcome Dr. Christian.
Well, thank you very much for those kind words. It's always a great privilege to be invited to give such a lecture and to be invited here. I should say that whenever you're asked to give a lecture like this, of course, after your first thoughts of gratitude and so forth, the question that goes through your mind is, what on earth am I going to talk about? And after a little discussion, we decided, well, maybe we ought to talk about reliability. Now, this raises an interesting problem, because this is a subject that falls between 2 stools. It's not really geotechnical engineering, and it's not really reliability. So I ask you to bear with me today. Those of you who are versed in reliability theory are going to find my treatment of reliability methods somewhat superficial. And those of you who are versed in geotechnical engineering are going to find there isn't really very much in the way of soil profiles and standard penetration tests and so forth. We're really kind of where these 2 areas overlap. I should also mention that my wife is a lawyer until she retired, and so is my brother and my nephew, by the way. I seem to come from a family of lawyers. And one of them, incidentally, is the county attorney in one county near Waco, and the other is the district attorney in the nearby county. So anyway, we went to dinner one night, and a man gave a talk on the rather complicated subject. In the car on the way home, my wife asked me what I thought of his talk, and I said, well, it was very interesting, but it had an awful lot to do with the time value of money and things like that, and it really cried out for a visual aid or 2 He just talked for an hour. And she said, well, you have to understand, lawyers are very verbal people. They're not very happy with charts and tables and things like that. And then she stopped and said, but you guys can't even get up and introduce yourselves without showing a slide with your name on it and your address and everything. So with that, we'll show the first slide. Okay. Now, reliability, as you can see, has been a concern of engineers for some time. This event occurred in 1895 in Paris. One hopes the French railways have become somewhat more reliable since then. But clearly, this kind of situation has been of some difficulty for a long time. Let me also acknowledge a large number of people who have contributed to this subject of reliability in geotechnical engineering. This list is by no means exclusive. And if somebody is left off there, it's because of my ignorance and my error. There's no intention to leave anybody off or to insult anybody. But a large number of people have worked in this area, and I think we've had, I think we're going to have more in the future. I'd also like to acknowledge that there are two previous Terzaghi lectures which dealt with the issues of reliability and risk in geotechnical engineering, Arthur Casagrandi's lecture and Bob Whitman's lecture. Those dates, by the way, are the dates of the lectures, not the dates in which they were published, but they have been published, both of them, at least twice. Also, Suzanne Lacasse's lecture a couple of years ago dealt heavily with issues of reliability, although she has not yet written it up. It has not been published. Well, this is what I'm going to talk about today. First, I want to say a few words about the nature of uncertainty in geotechnical engineering. What is it? Where does it come from? What do we know about it? I want to touch briefly on reliability methods, although I really don't want to say a lot about that. That's the mechanics of the process, and that's been well written up. I then want to say some words about the meaning of uncertainty and probability, and about judgment and probability, and how all this works together in the conflict between intuition and analysis. I want to then say what I think is important in any of these analyses, and that is, what do you do with the results? That, frankly, is a problem in deterministic analyses as well. Some years ago, Professor Duncan and I had an argument in public on this subject, in which, because I had said that the most important person in a finite element analysis was the guy who would explain what the results meant. And he took issue with what I said. And some years later, he said, you know, you were absolutely right. I agree with you now. And I think it's true in this area as well. And then, of course, I have some conclusions. As we go along, I'm going to have pictures of some examples of what we're trying not to achieve, which is failures. This happens to be the right abutment of Malpasset Dam, which was a dam in France, many of you will know, not too far from the French Riviera. The reason why these failures occur is always the subject to a great deal of debate, but in this case it clearly seems to have been a failure to understand the importance of uplift forces in the design of the dam. If there's anybody who can be considered to be the father of probabilistic methods, it's Blaise Pascal. And Ian Hacking quotes him this way. I will read it to you. We ought to fear or hope for an event not only in proportion to the advantage or disadvantage, but also with some consideration of the likelihood of the occurrence. And basically, that's really what we're talking about here, that we ought to be considering not only bad events that might happen that we ought to design against, but how likely are these events to occur. Incidentally, when he made this statement, he was talking about being struck by lightning, but it applies in other areas as well. Well, we know that we live in an uncertain world. We know that there is uncertainty in geotechnical engineering. We know that the world out there is, we don't know as much as we would like to know about the world out there. So the question is, how do we deal with it? And there are several ways to do it. The first way is to ignore it. And don't chuckle. This is, in fact, a widely used strategy for dealing with uncertainty. It is kind of a wing and a prayer approach. You hope that when the dam fails, you're not employed there anymore. That literally happened in one case. I will not mention names. There was a rather prominent dam failure, and the fellow who was the chief engineer of the outfit that built it had the good fortune or the wit or the luck to retire about a year before the dam failed. So when the congressional investigations started, this was a federal dam, He happened to be conveniently located somewhere in Arizona or something like that, and was not involved in the failure. So that's a good strategy for avoiding this kind of problem if you can do it. The second approach is to be conservative. Now, and of course, that's really what we often do. That's why we have factors of safety and so forth, is to make sure we are conservative enough. The problem is, how conservative is conservative enough? Clearly, eventually, you can be so conservative that it's impossible to build anything. And therefore, you have to, at some point, put some bounds on this thing. You will always have tremendous arguments about whether you have been conservative enough. So in geotechnical engineering, we have adopted and become attracted to what we call the observational method. And of course, you all know what the observational method is. You do the best you can in your design. You then make measurements. You correct, alter your design or your procedures on the basis of your measurements, and you keep on going. Terzaghi, by the way, called this the learn-as-you-go approach. It was Peck, I think, who actually called it the observational method. This same technique, of course, has been adopted, or modifications of it, in many ways. The environmental community uses something called adaptive management, which is substantially the same sort of approach. You go along, you do your work, and as you learn more about the problem, you try to make adjustments, you adapt your approaches. What I'm going to talk about today is that maybe while we're at it, we ought to try to quantify the uncertainty. Now, this approach, the approach of using the observational method and quantifying the uncertainty, are not in conflict with each other. Obviously, one is a supplement to the other, so there's not a distinction there. But I think this is really where we should be going. Now, in his Terzaghi lecture, Casagrande gave this definition to calculated risk. He based this on a research of the literature, and I'll just read it. He said, "The use of imperfect knowledge guided by judgment and experience to estimate the probable ranges for all pertinent quantities that enter into the solution of a problem. The decision on an appropriate margin of safety or degree of risk, taking into consideration economic factors and the multitude of losses that would result from failure." And even though Casagrande did not discuss specifically probabilistic issues in his lecture, I think the definition is still one that we could live with and one that works quite well. Now, reliability-based methods have in fact been adopted in many areas of practice. I mentioned offshore platforms and structures. Jean-Marie Audibert is here in the audience, and of course, that's an area, as you well know, which has adopted reliability-based methods to a fare thee well. This lecture would be totally unnecessary in the offshore industry forum. But there are other areas which have seen the advantage of an explicit recognition of the nature of uncertainty. Dams, embankments, and levees, seismic hazard analysis. One of the difficulties with seismic hazard analysis is after all the probabilistic work is done, the results are usually then used deterministically, so we lose a lot of the benefits of the probabilistic work. Open pit mine slopes are increasingly designed this way. Nuclear waste repository studies are heavily probabilistically based. And then there is the vexed question of limit state design or load and resistance factor design, which has been widely adopted in the structural area, but which is a rather vexed topic in the geotechnical world. I'm not going to say very much about that, but I think it's a subject that first we have to deal with seriously, but second, I'm not so sure that just simply taking the structural approaches is going to work in geotechnical engineering. Another little interruption here. This is Vaillant Dam after the fact. What you have here is the Dolomite Alps, and this stuff here used to be up there, and it all came down, and there used to be a reservoir here, and the water in the reservoir went over the dam, which is on the other side of that little hill up there, and the water sloshed out and famously and went down the Piave River and killed about 3,000 people in a little village that was downstream of this thing. And there have been a lot of studies of this problem. Finally, some people have gotten some ideas about why the slide occurred, but at least as far as I can tell, nobody has been able to figure out why it was traveling as fast as it was when it hit the water. Clearly, this should be a concern to people building dams in the Dolomite Alps. Okay, let me say a few things about the tools that are available to us to do reliability work. There are the classic reliability analyses methods, first order, second moment methods, first order reliability methods, Monte Carlo simulation, and so forth and so on. There are event and fault trees. There are influence diagrams, and there are combinations of all of these. These, as I say, are well documented. There's a large literature on these techniques, and I don't think we need to spend a lot of time here today explaining how they work. The basic issue that we're getting at here is that if we have some way of determining or describing the load that a system will see, and some way of determining the resistance, we know these things have some kind of probabilistic distribution, that the margin of safety is the difference between the two. We can also work with factors of safety, but let me work with margins for the moment. Now, it turns out that if these are distributed in any kind of reasonable way, this also must have some kind of a probabilistic distribution which we can work with. And we can, by various techniques, evaluate the mean and the standard deviation of that margin of error. Those reliability methods are ways of getting at those evaluations. And then we define something called a reliability index, which is simply the ratio between the mean and the standard deviation of the margin of safety. Now, exactly how we actually go about calculating those numbers is a subject of some that we could spend a lot of time talking about, but take my word for it, it can be done. Now, if the margin is distributed this way, it could be any distribution, by the definition that I just used, the distance between the failure condition, which is the condition when the margin of safety is 0, and the mean is simply beta times the standard deviation. And the probability of failure is the area there. If I now look at the cumulative distribution, this is simply the integral of that, then the probability of failure is the intercept, where this curve intercepts the vertical axis here. Now, I haven't said anything about what those distributions are. If, in fact, this thing is normally distributed, and that's a reasonable assumption for a number of cases, then it turns out that the probability of failure is simply equal to the cumulative distribution function for the standard normal variate evaluated at negative beta. Now that sounds like a big mouthful, and it used to be something that you had to interpolate. Nowadays, any spreadsheet worthy of the name has this as a built-in function and takes you less time to evaluate it than it does for me to tell you what it is. So you can get the probability of failure directly once you have the beta, the reliability index. Incidentally, I should mention that in some cases you will see people show this area here as the probability of failure. It's not. I'm not sure I know what it is, but whatever it is, that's not the probability of failure. Okay. We can also use event trees and fault trees. And I just want to say what they are. An event tree is a technique for looking at a succession of events. An event doesn't have to be something happening, it can be a condition. In other words, the existence of a liquefiable layer can be an event. And what you do is you create a tree. In this case, a rather simple one. You start with an event, and then you look at the things that could happen, and they have to be exhaustive. That is, they have to include all the possibilities, and they have to be exclusive. That is, they can't have any overlaps between them. And you determine the probability of moving from this position to each one of these, and you keep on doing that down here, and you get the conditional probabilities. Then you multiply them all together, and that gives you the probability of winding up out here at the end of that train. You can do anything. You can analyze all kinds of things this way. I once did an analysis of the probabilities of winning a tennis match on the basis of the probabilities that an individual would win a particular point. Turns out very interesting that you get some counterintuitive results. Fault trees work the other way. Event trees go from left to right. Fault trees go from top to bottom. Fault trees start at the end, the dam breached in this case, and look at conditions that have to be satisfied for that to happen. And there are two kinds of situations that can exist. You can have a situation where both conditions have to exist before you proceed, or you can have a situation where any one of them, or more than one of them, can happen, and you proceed up that way. And there are mathematical techniques for working these things through, and you can combine event trees and fault trees, and there's a whole methodology here which can be worked out, and what it really is a way of forcing you to organize your thinking. This is a picture of Teton Dam in its full glory as it was ceasing to be a dam and becoming a flood. And this is another example of the kind of thing we want to avoid. Okay. Now, if we're going to apply these reliability-based methods, we have some requirements. And as always, there are four of them. First place, we have to have some input into this analysis. We have to have some methodology for doing the reliability analysis. We have to have some appropriate geotechnical analytical models, bearing capacity equations and that sort of thing. And we have to have some way of interpreting the results. Now, I've already said a few things about the methodology that we have for reliability analysis, so let's leave that alone. And I don't want to say anything about geotechnical analytical models other than to say that, in my opinion, the analytical models that are available to us as geotechnical engineers range from the excellent to the awful. Some of the models that we have, the analytical models that we have, are really, really bad and have really not been very well verified and have all kinds of built-in assumptions, and we use them without really understanding how bad they really are. Up there in the top of my list of things that really need some re-examination are the bearing capacity equations. But anyway, let's concentrate instead on the input first, and then we'll say some stuff about the output. Okay. First, I want to talk about the nature of uncertainty. Now, we've said things are uncertain. We know the world out there is uncertain. Okay. Now, what does that mean? And there are two kinds of uncertainty. These terms, aleatory and epistemic, I think were first used by a man named Hacking. If there may be somebody else who thought them up. And they describe two different kinds of situation. The first, the aleatory, is the situation in which you're dealing with what you might call a truly random process. That is, the name, by the way, comes from the Latin word for dice thrower. And it is the situation that you have when you throw a pair of dice. Now, in the best of all possible worlds, if we knew the velocity of the dice and their angular momentum and the modulus of restitution of the table on which they're thrown, you could calculate, I assume, what the dice would show. But realistically, we know that's not the case. And in fact, in the language, when we talk about a throw of the dice or a crapshoot or something like that, we know exactly what we mean. Something that we have no way of predicting. It's really, really random out there. There's just nothing we can do to predict it. We can describe the randomness. We can say what the odds are of getting various kinds of dice, but there's nothing we can do to affect it. The second kind of uncertainty, which comes from the Greek word epistemic, which comes from the Greek for knowledge, has to do with the situation where the world out there is fixed. It is what it is, we just don't know what it is. And the example is the arrangement of cards in a deck of cards after you've shuffled them. Now, I can tell you exactly what the arrangement of the deck of cards is. All I've got to do is turn them over one at a time. Now, unfortunately, you don't let me do that when we play cards. But I could, in fact, tell you exactly whether it's there. There's no uncertainty in the arrangement of the deck of cards. The uncertainty is in my knowledge of the uncertainty of the arrangement of the cards. And I ask you to think a minute about how you play cards. Now, I assume some of you here play bridge, for example. And you will know that the whole thrust of the play of that game is to elicit knowledge, to elicit information from the bidding and from the play of the hand, so that a good bridge player early into the hand knows exactly where all the cards are distributed, because he or she has gotten knowledge, gotten information from the way other people have behaved. The same thing is true of poker, by the way. And you you have reduced your uncertainty. You've reduced you've made your knowledge better by gathering more information. Now, the way you deal with these two kinds of uncertainty is very different. For this one, you can't do anything to reduce it. You can describe it, but you can't do anything to reduce it. This kind of uncertainty you can do something with, because the more information you have, the more you can reduce the uncertainty. And I submit to you that this kind of uncertainty is what we're dealing with, by and large, in geotechnical engineering. The geologic profile that we have out there is there. There's only one of it. And it's there, and it is whatever it is. The problem is we don't know what it is. And most of our efforts, or a lot of our efforts, are aimed at trying to figure out what's there. The second distinction that we need to bear in mind is the meaning of probability. Now, you can derive all of probability theory from three rather simple axioms. The only trouble is that nowhere does it tell you what probability is. It's just a thing, P. And so what do you mean when you say something has a certain probability of occurrence or of existence? Well, you can mean two things. The first thing you can mean is that it's a measure of the frequency with which things happen. I go out and I count things, like automobile accidents or something like that, or a number of times that teams that are 3 games behind in the American League Championship Series win the series and that sort of thing. And I then compile these statistics, and out of that I say, well, this is a measure of some underlying probability. There's something out there in the world that's called probability, and we're trying to measure it, and that's what we're doing. The second approach is to say, wait a minute, in most cases we don't have repeated experiments. If, for example, a few days ago we had a discussion of the probability of the Red Sox winning the World Series, we could have, that would be a meaningful discussion. Today, that's not a meaningful discussion. They won. You know, the probability of their winning the 2004 World Series is 1. They were successful. Furthermore, we're not going to repeat that experiment. And that's true of many things that we do. We don't have repeated trials. We only have one trial, or a small number of trials, and so therefore our probability is based really on a degree of belief about what is going to happen or what exists out there, not on repeated trials, and therefore there is no probability that lies out there that is a real thing that we are trying to measure. It's in our minds. Now, this all sounds very abstract, but let me point out something. Consider the insurance company. You go to the insurance company to buy insurance for something or other. The insurance company employs a building full of actuaries who are there to calculate the odds, the probabilities that you will die or that you will have an automobile accident or whatever it is that you're insuring yourself against. And they do this on a frequentist basis. In fact, if you go to the insurance company and ask them to insure you against something that they have very little experience with, they get very unhappy. They really don't know what to do with that. So the insurance company is a frequentist. On the other hand, you are a degree of believer. Because when you buy the insurance, you're insuring one life, yours. You're not going to have repeated trials here. You're only going to get one bite at that apple. And even if you're insuring something like your automobile, it's a limited number of trials that you're going to have there. You don't tend to have 15 accidents, in the next little while. You intend for this to be a very, very small sample. And so you buy insurance on the basis of your perceived needs, the needs of your family, what you would like to there are all kinds of issues, obviously, that enter into your buying insurance. But you're buying it on the basis of your perceived need, which is your degree of belief in the probability against which you're being insured. The insurance company is a frequentist. You are a degree of believer for the same transaction. Furthermore, when we do soil testing, when we process laboratory data and we have frequency diagrams and means and so forth, we're being frequentist. When we're carrying out an exploration program, what we're really trying to do is to sharpen our degree of belief. Usually we start a field program with some model of what's going to happen out there, and as we get more data in, we modify that model, and we are acting as degree of believers. Okay. And finally, let me talk about the difference between frequentist and Bayesian statistics. The term Bayesian statistics has become very fashionable these days. Even The Economist had a section on Bayesian statistics about a year ago. You can use the term to frighten small children and other such things. Now, frequentist statistics are the kind of statistics that if you have taken a course in statistics, that's what you studied, probably. It's the kind of statistics in which you have null hypotheses and so forth. A subject which is mind-bogglingly confusing, and which has a notation which I've often thought was intended not so much to help convey information, but to prevent you from entering the temple. And anyway, what most people don't understand about traditional statistics is that when you, and by the way, things like geostatistics and various kinds of regression analyses, discriminant analyses and so forth are all examples of standard frequentist statistics. And what you get out of this, if you say do a geostatistics evaluation of a profile, and you come up with certain probabilities, what those are is the probability that given the underlying model that you are trying to verify, you would observe the data. So it's the probability of observing the data given the model. Okay? Now what Bayesian statistics give you is the probability that the model is correct given the data. And I submit to you that that's what you really want. What you really want to know is the probability that there is, say, some kind of a fault or some kind of a failure mechanism out there that might cause trouble. You don't want the reverse thing. What is the probability of observing these data if the fault is there or if the model is there? In fact, this is a quotation from one of the many Bernoullis, who wrote, even the stupidest of men by some instinct of nature is convinced on his own that with more observations his risk of failure is diminished. And this is the essence of Bayesian approaches to reliability. Now I have here an example, and this is kind of Bayesian updating 101. It is the simplest example I can think of. It is an insult to anybody who's actually done Bayesian analyses, so those of you who are out there who have done them, bear with me. But it, I think, does illustrate some of the kinds of things that happen when you use this kind of approach. Let us suppose that we have, I should say also that this example is not entirely hypothetical. We actually had a case in which this, on which this is based. I think Jean-Marie may remember this incident, but I will not mention further what it is. Let us suppose that we have a soil profile out there, and we would like to know what is the probability that there are some zone or zones that are liquefiable. Now, that means by some measure we do CPTs or SPTs or something like that, and we're going to get some sort of a measure of whether this is liquefiable or not. And the question is, what is the probability that it exists? And how is this affected by successive borings? I go out and I make a boring and I get some information, and what does the next boring tell me that helps me to answer that first question? And finally, are more borings necessary? Well, let me assume the following. I'm going to assume that we're doing this with standard penetration test, and because of the configuration of the test and because of the way the zones are distributed and so forth, that there's about a probability of 30% of detecting the zones or zone in any one particular boring. that means there is a 70% probability of not detecting it in any one particular boring. Let me further assume that we all know that we can get false positives. You know, by various, because the driller makes mistakes, we can often get low blow counts in standard penetration tests or in other kinds of tests. So there are situations in which we might get an indication of a weak zone even though it's not there. And so therefore, let's say there's a 5% chance of finding it even if it's not there. And there's a 95% chance, of course, of not finding it if it's not there. What this notation means is E means it exists, F means we find it, and the bar over the top means not. So this means the probability of finding it if it's not there. I mean, I understand finding, I guess, has to be in quotations in that situation. Okay, now let's assume that we have, I'm really neutral about this. I don't know whether the stuff is out there or not. So I'll say, well, all right, there's a 50-50 chance this thing exists. The probability that it exists is 50%. Now, and let's assume that I find it, or I get an indication that there is this liquefiable zone in the first boring. And this is the so-called Bayes' law. Again, you needn't worry about exactly how this gets derived, and it looks perfectly awful, but it really is fairly easy. It turns out that you plug in the appropriate numbers in this equation, and what it gives you is that if I detect it in one boring, I can then say that there's an 86% chance that the thing is really there. I'm getting to improve my knowledge a little bit. Let's suppose I don't find it in the first boring. Well, then I go through the same kind of analysis and I discover that there's only about a 42% chance it's there. In other words, I have reduced it from 0.5 to 0.42, but that's not very much. In other words, there's still a very substantial probability that there is a liquefiable zone there, even though I didn't find it in the first boring. And I can keep on doing this, and this, let's suppose we have 3 borings, and this is all the possibilities. You know, you find it, and then you don't find it in the next boring, and you found it in the next boring, and so forth. Turns out it doesn't make any difference what order you do these things in. And you can see if I keep on finding it in the borings, why I get pretty darn confident that the stuff must really be there. If I find it in 2 borings, but I don't find it in the other ones, I'm still pretty confident. If I don't find it in any of the borings, my belief that it's there is reduced, but not nearly as much as you would think. I still have something like a 30% probability that there's a liquefiable zone there, even though I didn't find it in any of my borings. And in fact, you can do this for all the cases. We started with a probability of 0.5, and those are the results that we got after 3 borings. And there are 3 possibilities. We don't find it in any borings, we find it in 1, 2, and 3. And I think you can see that if you find it in all 3 borings, regardless of what you thought initially was the probability that it was there, you get to be pretty darn confident that it really exists. If, on the other hand, you don't find it in any borings, the amount you deviate from a straight line inclined at 45 degrees is pretty small. In other words, not finding it in 3 borings doesn't really buy you all that much additional information. I submit to you that this is the kind of thing that happens a lot in our construction projects, that we find, we all know of nice surprises that have happened during construction, even though we had very nice boring programs and very nice exploration programs. The particular instance I'm thinking of, they had the entire excavation dug before they found out that they had liquefiable soil underneath it, and the Frankie Pile Company was delighted because it was the largest, densifying that stuff was the largest Frankie Pile job in North America at the time. Okay. All right, another little interruption here. This is the St. Francis Dam. The morning that it was filled to capacity, or the morning before it was filled to capacity, this is what it looked like the next morning. That was, there's still arguing about why that dam failed, but clearly that was not what was intended. Okay, let's say a few things about how we go about getting soil properties. Now this, we've all seen pictures like this, index property, field vein, and so forth. And in this case, we have 3 zones, a marine clay, a lacustrine clay, and so forth. Now, let's concentrate for a moment on the field vane strength that has been measured. And I submit to you that if you had to choose the field vane strength that you would use for the marine clay, that you would probably choose some sort of an average value through there, and you'd be pretty happy, pretty confident with using that number for your analyses. On the other hand, when you come down here to the lacustrine clay, you've got a problem, and that is that, yes, you could put an average through there, but it would, there'd be a lot of scatter around there. You'd have to accept a large uncertainty in that value. So you could put maybe some kind of an inclination, a slope in there, or maybe even some sort of a higher order curve through there. Now, if you put some sort of a higher order curve, a curve with more parameters to describe it, you would reduce the scatter about the curve, about the values that you're using. But you would also increase the uncertainty in the parameters that you're using to describe the variation of the strength. In other words, you'd be much more confident of the location of a mean value than you would if you put some sort of a curve through there. So the trade-off between the two kinds of description of this error, between the systematic error, namely the location of the mean, and the scatter about that error, is a trade-off. You increase one at the cost of decreasing the other. Furthermore, and this is, I think, the important point, this is not an aspect of nature. It's a modeling decision. How I choose to model that stuff is a choice I make. The data come from nature. But to say that, suppose I put a uniform, I assume that there was a mean value and that's what I'm going to use as a uniform value and there's a certain scatter about it. And somebody else says, no, I'd rather use a more complicated description of that variation and I'm going to have a smaller amount of scatter. The difference between those two statistical descriptions are purely modeling decisions. It's not that nature has changed between those two. I made the decision as to which of those two I would like to do. And so a lot of these choices we make that lead to descriptions of error are modeling choices, they're personal choices, they're not the result of nature. And this chart has been around for a while. When you look at the uncertainty in properties, it really comes from, there are two things you can divide it into. One is data scatter and the other is a systematic error, which is what we just discussed on the previous slide. This is the mean trend, or then this is the scatter about that trend. And these can be further broken down into the real spatial or temporal variation. And then there's always random testing errors, which you'd like to get rid of. They're small scale errors, and there are techniques for doing this. The systematic error can due to a real statistical error in the trend. That's something that happens when we do any measurement. And then, of course, there's bias in measurement procedures. You'll notice those data that I had before were field vane data, and we all know we have to correct those field vane data on the basis of plasticity index. And those data can vary a little bit from that correction itself has a lot of uncertainty with it. So there's a certain element of that enters in here. Now, what's important here is that this kind of error propagates all through the system. If I'm doing a bearing capacity analysis or a settlement analysis or a slope stability analysis, those errors propagate all through, and they're with me all the time. This kind of error tends to average out. If you do, for example, a slope stability analysis, and if you look along the failure surface that you're using, that the strength may be high or may be low, it kind of averages out over this. So this kind of error tends to get averaged out in our analyses. This kind of error sticks with us, and it's important to separate out the two, even though it may be the result of a modeling choice. Now, let me say a few more things about measuring properties. Let me say that I have measured the shear wave velocity of a deposit, and I get these numbers. Now, if I calculate the mean and I calculate the standard deviation, that's what I get. Now, there's kind of an assumption that we make when we do this that these things are normally distributed. They may not be, but let's say that they are. Now, I haven't told you the whole story about this. These are not real data. What these are is 6 values of shear wave velocity that I generated with a random number generator because I was trying to look into something else. And I generated them from an underlying normal distribution. This happened to be the first 6 that I generated. And the properties of the underlying normal distribution were that the mean was 240 meters per second and the standard deviation was 24. Or if you want to see this in a picture, this is the distribution I generated them from, and this is the distribution that's implied by the means and the standard deviation of the data that I got. In fact, when I first got them, I thought I must be doing this, the random number generation wrong, because this was so far from that I had a hard time understanding. No, this is what happens. If you only have 6 data points, you are going to have trouble. You are sometimes going to encounter cases in which the implication you get from those data are not really very good. And so when if out in nature there is something that's normally distributed and you only measure it 6 times, you got a really good chance of getting it wrong. There's 2 guys who became rather famous, Hon.M.ASCE and Terzaghi, and some years ago they wrote a paper in which they talked about the law of small numbers. You probably have all heard of the law of large numbers, which says if you go out and measure things and take a lot of measurements, eventually your measurements will converge on the underlying distribution. The law of small numbers is that people like to believe it also applies when you've got small numbers. And of course, it doesn't. So be warned, unless you are collecting hundreds of data points, you're going to have problems like this. Now let me talk a little bit about expert elicitation and expert judgment. We all know what experts are. We are experts. You know, we get asked questions about things and we give pronouncements on things, including trivial things. But there's a large literature on this subject. A lot of people have looked into how good experts are. Now this is a case, a fairly well-known case actually, in which there was an embankment north of Boston, the I-95 embankment, which was abandoned. And the idea was that they were going to go out and they were going to pile more dirt on top of this thing until it failed. And they invited 7 experts, and these folks were really well-known guys. And they were asked to give a bunch of estimates about what was going to happen. And one of the things they were supposed to predict was how much additional fill would be necessary to bring this embankment to failure. And they were also asked to give 50% confidence limits on their estimates. In other words, they were supposed to tell the people running the program an upper and a lower bound, and or an upper quartile and a lower quartile boundary, and that they would say that they expected that 50% of the time the actual result would fall within that range. Now the actual amount of dirt that it took to fail that thing was 18.7 feet, and that's what this thing is here. This dotted line here is the average of the best estimates, which are the red dots. And you'll notice that the average of all 7 experts is pretty good. In fact, what's really critical in this case is not the incremental amount that it took to fail it, but the total height of the embankment. And so the experts did a pretty good job, on average. However, notice that in no case did the actual amount that it took to fail the embankment fall within any expert's 50% confidence limits. The actual amount that it took to fail the embankment did not fall within any expert's 50% confidence limits. Another example. Now this is a case in which 9 designers were asked to design foundations for transmission towers. And then there were 6 foundations designed, six of these foundations. And then each of the foundations was failed, and in this particular case, the pull-out load is the important load, and so these were pulled out. And for each expert, they calculated the mean of the ratio between their predicted capacity and the actual capacity. Notice that if this number is less than 1, that means the expert was conservative, because P over Q is less than 1. And the red dots here are the averages of all 6 for each expert. And the lines are the bottom and the top. And these are arranged in this order because the paper from which I got this happened to arrange them in order of decreasing goodness. And so that's why there's that trend. Now notice that these two fellows did pretty well here. They tended on average to get things pretty well. Notice, however, even this guy who was ranked number 1 by the folks who wrote the paper was about 30% conservative in this case, and about 20% unconservative in his worst case. So he had a pretty healthy range of goodness in his estimates. You might also ask what separated these guys. Well, it turns out that there were all kinds of different things. This fellow here had a master's degree. I guess that's in view of our meetings this morning, that should be an encouragement. He also had a lot of experience, and he had in fact participated in a similar program some years before, in which they had made some predictions and then actually tested things. This guy, however, had 30 years of experience and basically nothing else to bring to the table. So, you know, there wasn't too much difference between them. And then there were all kinds of various other things over here. I should point out that these folks down here tended to be the ones that had master's degrees and nothing else. So education all by itself clearly wasn't the thing that made you a better expert in this case. But clearly there's a real issue here about how good experts are in making this kind of an expert. Clearly people tended to be unnecessarily conservative if they made any kind of mistake. Okay, let's just summarize this by saying that spatial and systematic variances reflect a modeling choice and have different effects. That the values computed from small samples can be misleading. And that experts tend to be more confident than they should be. They tend to underestimate the variance in their estimates, how far apart. And this is true across the board. It's not just geotechnical experts. It's even people who estimate the scores of next Sunday's football games. Their experts tend to be a lot more confident than they really ought to be. And this gets us to the subject of engineering judgment, which we are all in favor of. However, it seems to me that we put ourselves in a really dangerous situation if we simply use engineering judgment as a word, as a pair of words, and don't base it on evaluated experience. In other words, if it's not based on actually going out and looking at what's happened the last time out and changing one's opinion on the basis of observations, engineering judgment can be a really dangerous thing. And a word of warning, I noticed my two lawyer relatives are in the back of the room there. I would not recommend that you use the phrase engineering judgment in a courtroom unless you happen to be prepared to defend yourself against the opposing attorney. In other words, it can be a euphemism for speculation or guessing, and you really don't want to be in that position. Here's another little interruption. This is the Old Man of the Mountain. It's in New Hampshire. It's on their license plates. It's on their quarter, or at least it was, because one day they came to work, and that's where it was. Okay, let's say a few things about interpreting results. And out of all this analysis, we get a probability of failure, and I put failure in quotation marks because failure can be a lot of things. It can be excessive settlement. It can be any kind of unexpected bad behavior, and so we know what we mean by failure. And the first question is, what is the allowable probability of failure? Well, you know, if you go to the public and you say, gee, what's the allowable probability of failure? It's 0 or very, very small. But that's not really a very realistic thing, and so we need some handle to deal with this. And one way to do it is to use what's called an FN plot. Now, this is Greg Becker's FN plot, and so Greg once said that this plot is the most widely replicated thing he has ever used, and every time it's used, it's in somebody else's paper, so he never gets credit for it. But anyway, what's done here is that people have looked at he has looked at various kinds of failures. And he's looked at the dollars lost and the lives lost. Now, unfortunately, this kind of implies a dollar value of a life, and that's not really what he intended to do. And then looked at the annual probability that these events, that this sort of failure would occur. And you notice that this thing this is a log-log plot, so there's a lot of scatter in it, but you notice that what you tend to find is that things that have low costs tend to have higher probabilities of failure, and things that have high costs tend to have lower probabilities of failure. And they fall kind of along a trend here. Now, you'll notice that these are his data, so if you have questions about it, you have to ask him. But for example, when he did this, he found that supertankers and mobile drill rigs were somewhat more risky than the general trend of this thing. Commercial aviation was way down here. We all know commercial aviation is a great deal safer than almost anything else that we do. And so this kind of gives you an idea of where to fit in one of these probabilities of failure. You can look at the probability of failure and what the cost might be and see whether this fits in with what is generally with this kind of a trend. Now, I would argue that this kind of a trend really represents what society has decided it's willing to accept. Other people will disagree with this, but the very fact that we do this and we build dams and foundations and mine pits and so forth, with these observed probabilities of failure and cost of failure, suggests that we as a society, kind of a society writ large, are willing to accept this kind of thing. Now, you can do interesting things with this. For example, we have had 2 failures of the space shuttle over a period of about 22 years. Each one killed 7 people. And that's about 0.1 failure per year. And 7 people means that space shuttles are kind of up here, which suggests getting on the space shuttle is a very risky proposition. And something that maybe should be done by trained astronauts who presumably are aware of this sort of reason. It does suggest that maybe we shouldn't be encouraging school teachers to get onto these things. Although it also suggests that maybe we should continue the politician in space program. Now this kind of insight has been used by a number of people. This is the Hong Kong Planning Department. They have a version of this. In this case, it's fatalities versus the number of events. The Netherlands people have another version of the same sort of plot. The Australia, New Zealand dam people have a version of this plot. And each one of these, the idea is that you give this to the designers and say, look, you go through one of these reliability analyses, and if you find yourself down here, you're okay. If you find yourself up here, that's not okay. And if you're in this region here, well, then you have to go back to the drawing board and do a little more thinking about whether you're really willing to live with that. Current thinking is that these really shouldn't be very bright lines, that there should be a kind of a fuzzy zone in there. And also, these are somewhat old plots. They've been updated recently. But this kind of thinking has now permeated a number of regulatory and design agencies. Now, there are certain problems with absolute probabilities. The first problem is that the one thing that is not considered when you do one of these risk analyses is all the things you didn't consider when you did the risk analysis. And if you look at failures, you discover that, of course, an awful lot of them occur because of something nobody thought of. Obviously, if you didn't think about it when you were doing the design, you're highly unlikely to think about it when you do the risk analysis. So there's a lot more risk out there that you didn't consider, and so therefore these probabilities are probably lower bounds. Professor Rosofsky was telling me at lunch today that there is a new kind of reliability or uncertainty in addition to regulatory and epistemic. It's called ontological, which is this issue, the uncertainty due to what we don't know, due to what we ignore. Okay. The second point is that people have a lot of trouble with small probabilities. There's a lot of evidence to suggest that folks are able to deal with things up to or down to maybe about 1 chance in 10. And once the probability gets lower than that, they have not the foggiest idea what that means. And I don't mean just the public. I mean engineers, scientists, nobody can deal with probabilities that low. And you need some mechanism like the ones I was just showing you in order to deal with them. Well, this suggests that maybe another way to deal with these things is to look at comparative probabilities of failure. And this is an example. These were 3 dikes, 3 designs for dikes. 6 meter, 12 meter, and this 23 meter was a multiple stage dike. The idea was that we're going to build the first stage, let it consolidate with drains in there to improve the strength, and then build the rest of it. And the question was, well, what were allowable factors of safety and what was going to happen here? Well, if you did one of these reliability analyses, you discovered that the expected values of the factors of safety were these numbers. Again, we all know that we shouldn't believe these numbers, the second decimal point there. They're all kind of substantially the same result. However, the probability of failure that's calculated from there is very different. This has a probability of about 2 times 10 to the minus 2, and this one is 7 times 10 to the minus 4. This one has a great deal lower probability of failure than the other ones do. And the reason is the failure is so broad that all the spatial uncertainty averages out over it. You can do some mathematics on that if you're willing to make some assumptions about how the standard deviation of the factor of safety varies as you change parameters. You can change those around so you can say, well, now look, let me look for some target factors of safety there. 1 chance in 1,000 of failure is probably something we can live with for an embankment, a dike, for a structure like that. These are much smaller structures. We can fix them pretty easily, so maybe we'll live with a probability of 1 in 100 for those. But failure of this guy would be a real mess, and so we want to make maybe 1 in 10,000. Well, if we work those through, we can then find out what the target factors of safety, the target expected factors of safety are for these 3 different designs, and these are the numbers you get. Notice that they are in exactly the reverse order of the expected probabilities of failure. A very counterintuitive result, but one that in fact comes out of the mathematics. And another thing we can get out of this kind of approach is contributions of different components. The same problem, this is the 23-meter high dike, and there are 6 contributions to the uncertainty here. The strength of this, the intact strength of the clay, the 2 clays, the strength after they were consolidated due to the drains, the friction angle of the fill, and the unit weight of the fill. And the bars, the blue part is the systematic error, the contribution of the systematic error to the variance of the factor of safety. This part up here is the contribution of the spatial error, and the reduction from there down to there is due to the averaging effect over the failure surface, which I told you is substantial in this case. Now notice, what this tells you is that you really want to look at the strength of the clay, this lacustrine clay, intact and consolidated, and the unit weight of the fill, amazingly enough. It turns out that those are the things that are really contributing to your uncertainty and therefore to your probability of failure. You really don't want to waste your time looking at these other 3 guys. Even if you've got them nailed down completely, it's not going to help you very much. So if you're now looking at where should you spend some money to improve things, to get a better feel for it, the analysis tells you where you ought to go and is a real guide to you in future work. Okay. This is the Chuquicamata open pit mine. That thing is about 800 meters deep. It is a big hole in the ground. And it's got, there's a fault that runs right through the middle of it. And you can see that the slopes over here look a lot better than the slopes up there, and that's because of the dip. The material tends to dip this way, and also there's different material on both sides of the fault. And in designing these things, by the way, you can see little things like that. Those are monster mining trucks. You know, those big things that you don't even let on the highway. You can't even see the pickup trucks that are here. This thing is unbelievably big. And they use, routinely now, are using reliability methods in order to design these slopes. You want them to be as steep as possible for economic reasons, but if you make them too steep, you're going to bring them down. Okay. Let me conclude then by, I've had several conclusions to this talk as I went along, but I want to end with a few points that I'll try to leave with you. First is that probability is not a property of the world, it is a state of mind. It is something, it has to do with the way you perceive the world around you. And second, that geotechnical uncertainty is primarily epistemic, it's Bayesian, and it's belief-based. And those are what we have to use in order to deal with it. And finally, I think the current challenge to us as a profession is how to use probabilistic methods in practice. And as in some areas, like the offshore world, that's already happening. But I think we need to, that challenge faces us as a profession. And I end with a picture of the La Conchita slide, which we used as the cover of our book. This is the slide, and I suspect the folks down here had a lot more belief in geotechnical unreliability after that thing came down in their neighborhood. And I think that's all I have to say. And if there are any questions, I'll try to answer them anyway.
I have a request, actually.
Yeah.
I think that we should talk about probability of success rather than probability of failure.
Well, yeah, but that's about 99 and a bunch of decimal point with a lot of nines after it.
But
people have as much trouble with that as they have with the small numbers.
But I think psychologically, it feels a lot better.
Yeah.
The minute you tell a client there's a probability of failure of, he may not even hear the number, he senses that there's a probability of failure.
Sure, and well, there's a wonderful story told about this, that some years ago, two guys and a girl actually, did a study of dam failures. This is not long after the Teton Dam failure. And they looked at the historical record for dam failures. And they concluded, and turns out there are records all over the place, although they're hard to dig out. And they concluded that the probability that any one dam would fail in any one particular year is about 1 in 10,000. So, in other words, there's about these are engineered dams we're talking about. It's a lot higher when you're talking about something that was just thrown up by the Boy Scouts last week to make a new lake. And this has some very interesting implications, because if you're doing a cost-benefit analysis for one of these dams and somebody comes along and says, by the way, there's a chance of 1 in 10,000 every year that dam is going to fail, it knocks the cost-benefit calculations into a cocked hat. So they discovered, by the way, that the Bureau of Reclamation had just about exactly 10,000 dam years when Teton failed. There are a lot of other data out there to support this. So they presented these results to the Office of the Chief of Engineers, who were, as you can imagine, although they'd paid for the study, they were not really delighted with these results. And they were, in fact, furious. So after these results were presented, one of the senior people there said, well, what this shows is that the dams we've built are perfectly safe, and now they're even safer. So that's the ignoring the uncertainty approach.
Any other questions?
Would you make some comments about the failure of the Waco Dam? I think your relatives are from Waco, aren't they?
Well, they're right up there. They probably know more about it than I do. I really don't know anything about this.
It was a Corps of Engineers dam.
Yeah.
And they missed a formation, and I believe it's called the Pepper Shale. Mm-hmm. And it got wet during the construction, and the whole sucker failed during construction. Mm-hmm. And Casa Grande got involved, and it went on and on and on. And it was all over poor exploration.
Sure.
Or that was what the conclusion was.
Well, as I said, that little example that I gave about the borings, the liquefaction, is based on an actual event. What actually happened in that case was that we'd sent a guy out in the field, and we'd had a blowout at the foot of one of the sheetings. And he was sent out there to see to it that we fixed that. And he had a drill rig out there, and he wanted to see if there were any other cases there might be a problem. And he said that the last day I was there, the driller was going to go off the site, and I said, you know, I'd better take this hole down to bedrock, because sure as hell if I get back in the office and I didn't run the boring all the way down to bedrock, I'm going to get criticized. So he took the thing down, and the next sample that he took, he hit low blow count material. And we stopped the job, and no, it was all hell broke loose. And we had experiments, tests, borings, all kinds of stuff all over the site, and nobody had detected it before. So it's a real problem. There's a very interesting book. It's the 1987 volume of the journal Engineering Geology. The entire volume is devoted to this. And it's the proceedings of a conference that Jerry Leonard ran at Purdue in 1985. And the subject of the conference was the failure of Teton, Baldwin Hills, Vaillant, and Malpasset. And that was close enough in time to those failures so that the people who'd been involved in both the design and the construction and the evaluation of those failures were still around. And so they had all kinds of presentations about it, and they transcribed the whole thing verbatim. And it is an absolutely fascinating document. So you want to see raw psychology out there on the page with people defending their decisions and trying to explain how come they really knew what they were doing, even though this dam is now a pile of rubble downstream. It's there. It's really, really a fascinating volume, worth getting your hands on if you can do it.